Alright, welcome to lesson 9.5, where we're going to talk about error approximations. So remember how we looked at Taylor series and power series and how we could write these infinite series to equate the actual transcendental function? Well, if the series aren't infinite, well, you probably have some error, right? So today I want to take a look at how we can actually calculate what that error will be. And so one of the first things I want to take a look at is something called the alternating series remainder. So remember we looked at convergent alternating series in the last lesson? And we're trying to approximate them, right, using the sum. But we're only using, let's say, the first n terms, right? So a whole bunch of terms, not all of them. So what I want you to realize here is that the alternating series remainder says that if you're using n terms, then the error that you create, right? So once again, the error is the difference between the actual sum and your estimate or your approximation here. It says the error will be less than or equal to the absolute value of the next term. Okay? So the idea here is once again, if you have an alternating series, so remember this, back and forth, 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 you'll know that the error must be equal to or less than the absolute value, don't worry about the direction, of the next term. So to show you this, here's an example. Here is an example of a alternating series. Why do we know this is alternating? Negative 1 to the power of means the terms are alternating positive negative. 1 over n factorial, yes, the terms are decreasing. And I think if I take the limit of this, yes, it does as n goes to infinity, this thing does become 0. So we know this is an alternating series. Let's quickly approximate the sum by using the first 6 terms. So all you need to do is just plug in the values of 1, 2, 3, 4, 5 to 6. Okay, so we'll approximate this sum. So remember, we need to have proper notation here. If I'm going to use this and say an approximation, then please use the squiggly equal sign. My first term here, when n equals to 1, so the exponent is positive, and 1 over 1 factorial, that's just 1. This next one will be negative, and this will be what? 1 over 2 factorial, so that's just 2, plus 1 over 3 factorial, which is 6, minus 1 over 4 factorial, which is 24, and then plus 1 over 5 factorial, which is 1 over 20, and the sixth term, so that's 1 over 720. So remember, this is 6 factorial. Okay, and if I asked you to actually approximate what this is, I would just ask you to use your calculator and actually calculate this. 1 take away a half plus a 6 minus 1 over 24 plus 1 over 120. And just to let you know, if you want to use the factorial notation, I can go 1 divided by, and then I think I use the math button. I don't know if you see this. Yes, math, and go over to probability, PRB, and choose number 4. That's where we'll get that absolute, or the factorial button from. So I forgot the number 6. Let me try it one more time. Probability 4. There we go. And boom, there's your answers. 0.63194. Repeat it. Okay. Now, my question in example number 2 is asking, well, can you actually find the upper bound for the remainder for the approximation? And remember how we said that the remainder is really equal to the absolute value of the next term. So what is the next term here? The next term will be the, yeah, that's right, the 7th term. And I just want you to have the remainder. So remainder is, I'll say, less than or equal to, that's what it says up here, the absolute value of the 7th term. So I'd just be doing negative 1 to the power of 7 plus 1 all over 1 over 7 factorial. This actually just becomes 1 over 7 factorial. And I would just plot that on the calculator. So 1 divided by 7, math, probability, number 4, press enter. Oh, wow, really, really small. That e to the negative 4 is times 10 to the negative 4. So think about taking 1 point, what was it, 9, 8, and then go 1, 2, 3, 4. So 1, 2, 3 zeros in front. Okay? Very, very small error. Okay? But that is the upper bound for the error. Okay? Or for the remainder, sorry. Okay? And then with this, can I ask you now to try to find the upper and lower bounds for the actual sum? Okay? So once again, we did all this stuff and we found that, hey, after 6 terms, I have this particular value, s sub 6. And then now adding the next term would require me to go a little bit further. Okay. So what are my upper and lower bounds? I hope you can see that the lower bound is really just s sub 6, or the partial sum of the 6th term. Well, that'd be 0.63194, right? Now, what would the upper bound be? Well, you just showed me in example number 2 that the largest error is that value of 1 over 7 factorial, or 0.00198. So my upper bound would be that value, that is the sum of the first 6 terms, plus the actual maximum error that I calculated from example number 2, 0.000198. And that is equal to 0.63214229. Okay. So if I ask you for the upper and lower bounds, yeah, you can just look at the sum and then use the remainder to help us figure out the other one. Okay. Now, once again, my lower bound was the actual sum, because I hope you can see that back in the example number 1 here, remember that last term here was a subtraction. So remember the idea of going back and forth, back and forth? I just went back. So therefore, my next term will make it going forward. Okay. If this was actually a plus sign, then of course the sum would be your upper bound, and you have to subtract the error to get the lower bound. All right? Okay. So a few more questions here. Example number 4. Another series. This time I want you to approximate it with an error that's less than 0.001. Okay? So just like example number 1, I think the best way of doing this would be to actually plug in the values. And I will just continue to find the partial sums along the way. And then hopefully you'll find a place where the error between two partial sums is actually less than 0.01. Okay, so here we go. When n equals to 0, this one starts at 0. Negative 1 to the power 0 is 1. 2 times 0 factorial, well, 0 factorial is just 1, okay? So that's just equal to 1. Our next term will be subtraction, so negative 1 to the power of 1, which would be negative 1. And then 2 times 1 is 2, so this is 2 factorial. And then I'll have 1 over 4 factorial, 1 over 6 factorial, and I keep going, but I'll just do up to 8 factorial. See what happens. Okay. Remember, 2 factorial is just a half, 4 factorial is 24, and 6 factorial is 720. I'm just curious what that would be right now. Okay, so let's just go ahead and use your calculator. Let's try this. 1 take away a half plus 1 over 24 minus 1 over 720. And lo and behold, I get the answer of, oh, that's not too bad. So that up to there is, I guess I should put equal sign. What was it again? 0.54027. 54027 repeating. Okay. Let me say 8. All right. All right, now I'm going to add in an extra term. So what happens when I add in 8 factorial, 1 over 8 factorial? I'm going to do now plus 1 over 8 factorial. Where's factorial again? Math. Ooh, can't see it. Number 4. Oh, 0.54030. Okay, so I guess I can say with, I'll do it over here, with the 1 over 8 factorial term, the sum is 0.54030. Now remember, I'm looking for an error that's less than 0.001, and if you actually went and just did 1 over 8 factorial, you'll see that its value is actually less than 0.001. Okay, which means I didn't really need this little term here. I could have just estimated it up to this term and be good with an error that's less than 0.001 over 1,000. Okay. Now, I hope you were thinking, that example 4, that series looks quite interesting. It actually looks very similar to something that you've learned before called an elementary series. Yeah. Quickly look back at the previous notes. Which one does this look like? Well, I will tell you. Should I tell you? No, no, I shouldn't tell you. I should let you look, shouldn't I? Go look. You don't want to look, do you? It looks like what? Hmm. Sine? Cosine? E to the x? Remember how this one here? This was pretty much cosine of x. Yes, yes, yes. But you're like, it looks almost the same except for this term. Right. So it's not there in example number 4. Right? It's not there. Well, it actually is there. And you see how example number 4 is, I'll say example 4 is where x equals to 1. Because if I made this thing here equal to 1, 1 to the power of 2n is just equal to 1, and then you get example number 4. So in essence, I'm asking you really here, what is the actual value? The actual value of the series in example number 4 is actually cosine of not x, but cosine of 1. And if you put that into your calculator, cosine of 1, you get 0.54030. Pretty close. Actually, look, 1 over 8 factorial would have given me, an answer that was correct to 5 decimal places. But hey, still pretty good. All right? So ultimately, here is what I want you to understand. Okay? The alternating series remainder is always less than or equal to, and you're like, what is this? Oh, well, it's the nth plus 1 derivative evaluated at the center point C, multiplied by x minus c to the power n plus 1, all over n plus 1's factorial. It really is just the expression to describe the next term. Okay, so think about that Taylor series we did, right? The nth derivative of c, x minus c to the power n over n factorial. This is just the next term after that, so I replaced n with n plus 1. Okay, so with an alternating series, it's just the next term. Done. Okay. The hiccup comes if you don't have an alternating series. Then what do we do? Well, the method is slightly different and slightly harder, but still, I'm going to use the word slightly because it's not that bad. Okay? We now call this thing the Lagrange remainder, or Taylor's theorem's remainder. And if you look at the next box, and I want you to compare this to the alternating series one, everything looks the same except for one change. Can you see the change? Now you can't see the change for sure. Oh boy, bad color to use. But I hope you can see that there is a Z instead of a C when you're trying to evaluate the next derivative. Okay? So the only difference here is we're going to use this letter Z, and Z or Z is the x value between x and c, inclusive, so we can use the endpoints, which makes this derivative a maximum. Okay? So this is the only change, okay? Where in the alternating series, we can calculate the derivative right away at the value c, For the Lagrange remainder for any non-alternating series, then we have to look at the next derivative and look at the largest value of the next derivative in the interval from, I guess, x to c. Okay? So as in the alternating series remainder, the n plus 1 term of the Taylor series is used. However, we have to be more careful of how we choose that derivative factor. Okay? And to show you some examples of that, I'm going to ask you to turn the page. So once again, the idea is you want to choose a value of z. So once again, z is the x value, okay, in the interval, okay, usually from x to c, okay, as long as that value of z makes the derivative factor a maximum. Okay? This could be at the center of the interval. It could be at an x value where f is to be evaluated, or you actually might know the maximum value in advance. So for example, you know that the sine function and cosine functions always have a maximum value of 1. So you can just say, oh, if it's sine, I know, boom, I'm going to use 1. Okay, because I know the maximum is always going to be 1. All right? So let's take a look at these examples now that help us understand how to use the Lagrange remainder. So in example number 6, I want you to estimate e squared using a Maclaurin polynomial of degree 10. Wow, degree 10 for e to the x. So hopefully you remember the elementary series e to the x. That is equal to, or I shouldn't say equal, I should say approximately, because this is an approximation. 1 plus x plus, x squared over 2 plus x cubed over 3 factorial plus x4 over 4 factorial, and so on, all the way to the 10th term, x to the power 10 over 10 factorial. And so if I want to estimate e squared, then yeah, all I have to do is replace x with 2. 2 squared over 2. 2 cubed over 3 factorial. 2 to the power 4 over 4 factorial. All the way to 2 to the 10 over 10 factorial. And I'm sure right now you don't want to evaluate this, so I'll do it for you. 7.38899. Okay, so now my next question is, can you use the Lagrange form of the remainder to estimate the accuracy of this partial sum? So pretty much I want you to find the remainder, right, or the error. So the Lagrange remainder says it's going to be less than or equal to, and it's going to be the next derivative, right? It's the next f of the 11th derivative, because my previous one had degree 10, and then this crazy thing z, right? And then we still have this, x minus c. This is a Maclaurin polynomial, so really I'm taking it at just 0 all over, oops, did I say 10? I meant to say 11. All over 11 factorial. Okay? Now we know what the x value is because you said it, x was 2. So I can actually replace that x with 2. The tricky part here, and by the way, I also forgot something. I forgot the absolute value sign. Right? I should have the absolute value in it. But the tricky part is, what is this 11th derivative and the maximum value of the 11th derivative? Okay? So let's think about what this 11th derivative is, first of all. Well, I hope you remember that f of x just equals to e to the x. So really, the 10th derivative of x is also e to the x, which means the 11th derivative is also e to the x. Okay, that's good. And so now, remember how I said that x value is 2 and it's centered at 0? So I'm looking in the interval. Look in the interval from 0 to 2. And you want to choose the maximum value of the 11th derivative in this interval. And this is e to the x, so I hope you know what this looks like. It goes like this. And so where is the largest value going to be? From 0 to 2? Yeah, at the endpoint 2. So really what I'm saying is that z value equals to 2. Okay? So understanding that, I can now go back and evaluate this absolute value. F the 11th prime, that's not double prime, this is the 11th prime of z, would just be evaluated at z equals to 2. We know our x value was 2, so this is 2 minus 0 to the power 11, all over 11 factorial. And this is my error. I'm going to calculate that, and let's see what we get. So what do we have here? Oops. Oh, my calculator is off. E to the power of 2 times 2 to the power 11 divided by 11 factorial. Wow, that's totally small. That's what, 379, and then we're doing how many decimal places in front? 4, right? So 1, 2, 3, 4. 0.000379, and that's the error. Okay. Two more, and then we're done for today. So looking at example number 8, this time I've told you the fifth derivative of the function is 700 times sine x. And if x equals to 0.7, it is in the convergence interval for the power series of f centered at x equals 0. Okay, so we know it's in the interval of convergence. That's great. We know that this then converges. The question here says find an upper limit for the error when the fourth degree Taylor polynomial is used to approximate this. So you're using the fourth degree Taylor polynomial to approximate. So your error actually occurs using the next one, okay, which would be that's right, the fifth derivative evaluated at z times x minus, well, center at 0 again, to the power of 5 over 5 factorial. So once again, what is x? Well, they gave that to you. That's great. So x is 0.7. The tricky part here is what is the fifth derivative of something? And what's the largest this could be? Okay. Now here is where you have some choice. Remember how I told you, oh, sometimes you know stuff like sine and cosine? You could say, hey, this is a sine function here, right? I know that the largest value of sine x must be 1. So that is correct. And if you do that, then this thing in blue can be simplified to just 700 times 1, right? Because sine of x, so once again here, I'm saying sine of x, the maximum value is 1. And then you can just quickly evaluate this 0.7 to the power 5 over 5 factorial, and that would perfectly be fine. Let me just tell you that 0.9804. Okay? But, okay, but remember how I said you really should be using the z value here that is between x and c. So technically, if I'm thinking about this, x is 0.7, my c value, where it's centered at, is 0. So you really should be looking at the interval. Look, in the interval from 0 to 0.7, right? And because this is the sine function, hopefully you remember what it looks like, right? And it reaches its maximum at pi over 2, which is about 1.57. So I know that 0 to 0.7 is on this upward trend or increasing part of the sine function. So therefore, where would the maximum occur? Right? So I'll say since sine x increases in the interval from 0 to 0.7, the maximum occurs, yeah, where? At the endpoint, the right endpoint. So really, when I asked you to find the fifth derivative of z, maybe I shouldn't have been so generous and just said, oh, sine x's maximum is 1. Maybe if I wanted a more accurate answer, I should have done this. I should have said the Lagrange remainder is the fifth derivative of z, which would be 700 times sine of 0.7 multiplied by, yes, 0.7 to the power of 5 all over 5 factorial, where this now is the actual maximum value. And if I did this on the calculator, I'd probably get a better estimate, which means my error should be smaller. Let's see if that happens. 700 sine 0.7 times 0.7 to the power of 5 divided by 5 factorial. Yeah, 0.63156. So more accurate. Okay. Now, both answers I think would be fine. However, I think the one I wrote down in blue would be the preferred one, right? Okay. But sometimes, maybe it's a multiple choice question, you have no calculator, then definitely use that sine x equal to 1 as a maximum to figure out a question like this. Okay? All right, last one here, example number 9, before you try some questions yourself. Got the sixth derivative here, and it's telling you that it's a positive decreasing function. I'd like you to find the error bound when a fifth degree Taylor polynomial, this time centered at x equals to 4, is used to approximate f of 4.1, and assume the series does converge for x when x is 4.1. Okay, so notice it's centered at x equals to 4, so that's really your c value. And I'm asking you for 4.1, so that's your x value. This time it says I want you to use the error bound for a fifth degree Taylor polynomial. So once again, it should be, yes, the sixth at some z value, x minus 4 to the power of 6 over 6 factorial. And by the way, don't forget absolute values, which is what I forgot up here. Oops, I should go back and change that. Absolute values, still positive anyway, but yeah, to be proper, absolute values, please. Okay. And yes, what would this be now? I'm looking for the maximum value of the sixth derivative. So think about what these words mean. Positive decreasing function. So my sixth derivative function looks probably something like this. And if I'm going from x is 4.1 to the value that's centered at c, I hope you can see that where will be my maximum value? Not at the right endpoint this time, but at the left endpoint. So yes, I'll say since the sixth derivative is positive and decreasing, the max value occurs, that's right, at the left endpoint. And because I don't have a function for this one, all I can now do is just replace this with the sixth derivative at the value of 4. And this will be 4.1 minus 4 to the power of 6 over 6 factorial. Absolute value of that. We really don't need the absolute value because we know it's positive. But if you wanted to write this a little bit nicer, sure. The sixth derivative at 4, and this would be, what, 0.1 to the power of 6 over 6 factorial. Okay, and that would be the error for this example. Okay, that was a lot. Okay, I hope that this is kind of sinking in. Okay, you need to do some practice for sure. And I would seriously do a lot of practice here because the next part of the unit, or unit 9, deals with some different things. So we're going to leave these ideas of series for a bit. And so use this as a way to kind of end off the first part of the unit well. Okay? Finish strong. Do some practice.